Hello. Hello. Okay, so I'm going to begin in about a minute. Okay, so today is the last lecture of the course, and we're going to be talking about a couple of ideas and a couple of things that perhaps I did not focus on much at the start, but I would like to bring them in right now and talk about yet another factorization, yet another decomposition of a matrix, right? So far, we've dealt with nice matrices, we've dealt with diagonalizable matrices, and we've seen what we can do with matrices that are diagonalizable and not. One thing that I would like to talk about before I begin today's lecture is to talk about rank 1 matrices. So rank 1 matrices. And what are rank 1 matrices? The idea is, let's say if you have, well, you should know what a rank 1 matrix is. A rank is the number of independent columns or independent rows that you have. And a rank 1 matrix just says that you have only one independent column, which means something like this, which means if I have the following matrix 1, 2, 3, and 3, 6, 9, and 0, 0, 0, then this is a rank 1 matrix. And the idea is that this matrix can be broken down into something like UV transpose, right? So for example, I can write this as some vector times another vector's transpose. So I'm just going to write it out. I'll just say that the column that's independent is the U vector, and the row that I'm going to multiply it by is going to tell me in each of these columns how much of the column that I have, right? So if I write something like 1, 3, and 0, then you can see that the matrix that I will generate is the following. So this one tells me that I have, if you want to look at it in terms of rows, you can do that. If you want to look at it in terms of columns, you can also do that. So the first is saying just take 1 times the whole column. That's just 1, 2, 3. The second column is telling me, okay, just take 3 times the column. So that's 3, 6, and 9. And the last entry in the row is telling me just take none times, like multiply this by 0 and you get 0, 0, 0, right? And this matrix we know has only one independent column, which is this one, right? The 0 column is not an independent column. Okay, so that's a rank 1 matrix. And perhaps I can even do a similar sort of thing for, let's suppose, in a matrix which I have something like the following. For example, I have 2 independent columns, so 1, 2, 3, 2, 0, 2, and perhaps the last column is a linear combination of these two independent columns. So that's 3, 2, and 5. And so now if I want to write this in a similar form, maybe I can do, so I just write down the independent columns. So that's 1, 2, 3, and that's 3, 0, 2, sorry, 2, 0, 2. But now I ignore the last column because that's just the linear combination of the first two columns. And now this is a 3 by 3 matrix. This is a 3 by 2 matrix. And now if I want to get A back again, I need to multiply it by a 2 by 3 matrix. And all of this will work out very nicely. So I'm going to fill it with some rows that will tell me what combination of each of these to take. So if I look at the first column, I want 1 times the first column and 0 times the second column, right? Because it's just the first column. So I do 1, 0. And that gives me 1 times this and 0 times this, and add them together and I get this. The second column is just 0 times the first column and 1 times the second column. So you just get 2, 0, 2. And lastly, what you have over here is just 1 times the first column. You want to add them up, right? So this is C1, this is C2, and this is C1 plus C2. So you can think of C1 as 0 times C1 plus, sorry, C1 plus 0 times C2, and you can think of C2 as 0 times C1 plus C2. And so these are where the numbers are coming from, and the last number will just be 1 and 1. Okay, so you've sort of broken this rank 2 matrix into what I'm going to call the C and the R, which is a column matrix of independent columns, and a row matrix that tells you what combination of these columns to take to construct your matrix, right? And this is a very simple factorization. So A equals to CR is something that comes immediately out of the ideas of independent columns and constructing rank 1 or rank 2 matrix. So this was a rank 1 matrix. You can look at this even as C times R, where this is the C matrix and this is the R matrix. So it's not strictly the same dimension as A. That's only going to happen when you have n independent, right? So the dimension of this is going to equal to the dimension of A if and only if A has all columns as independent, because then you will need to write all the independent columns. And actually, in that case, if you have to write all of the columns, then this factorization doesn't really exist. It is just the full matrix, right? So what am I saying now? I'm saying if I have three columns which are independent, so 1, 2, 3, 2, 0, 2, and hopefully -1, 1, 0. Hopefully these 3 vectors are independent. And so what I get now, if I want to write it as C times R, I take, if all of these columns are independent, then the C matrix is just going to be equal to the A matrix. So I just take all the columns. But then what about the R matrix? Well, the R matrix has to tell me, let's say if we even try to construct this is already A. If I want to make this equals to A, I should only be multiplying this with the identity matrix, and that turns out to be the right formulation. So if I write the identity matrix here, it's actually a row matrix. You can look at it in terms of a row matrix telling me to take 1 times the first column, 1 times the second column in the second row, and 1 times the third column. So we get all of these. So you just get this matrix again. So this is sort of seeing A as A equals to CR when there are all independent columns, right? But otherwise, if you have fewer independent columns, you can write it in terms of those columns which are independent and get rid of the dependent columns. So that's a bit about low rank and full rank matrices. Okay, the next idea that I want to discuss is something that I briefly perhaps mentioned, and we talked about similar matrices. And now I want to look at similar matrices in the context of diagonalization, right? So I said that similar matrices are something like this, that A is similar to B if A is equals to M times B times M inverse. So I say A is similar to B. And that's the definition. And we also, if you recall, we looked at it in terms of a transformation that's doing the same thing, so transformation. doing the same thing, such as A, but now what we do is so if this is let's suppose B, then if I first multiply it by, let's suppose M, right, and that takes me into the same space, but slightly, so that gives me a different basis for the same space, right? And then A will do exactly the same thing, the same transformation, and then you can apply M inverse. So actually I've written this incorrectly. I should write this as it was correct initially. So A does some transformation, and M times B times M inverse does the same transformation, right? So this is a change of basis. Then you go into the B, you go into this transformation, and then you revert the basis. So you go back to the basis that A was working with. So the only difference is that they are working with different bases. And the nice thing that I then mentioned was that the nicest thing that could happen is that you get A is equals to X times D times X inverse, in which case what you have found is that this transformation actually gives you a bunch of eigenvectors which just get scaled due to the transformation. So the basis, you're working with a basis of independent eigenvectors. So now I want to look at, this is something that we've already talked about, and you can look at the previous video in which I mentioned these ideas, but now I want to look at them in terms of families of matrices. And so if I say similar matrices are sort of like the same family in which they do the same transformation for different bases, so A and B and D are all similar matrices, right? You can see that this format is being followed by the diagonal matrix as well. So A is similar to the diagonal matrix, and actually B is also similar to the diagonal matrix. So if A is similar to B and A is similar to D, you also get that B is similar to D. And you can check that out by just saying, okay, I can write this as, since A is equals to MBM inverse, then I can just say MBM inverse is equals to XDX inverse, and then I can just move the M's on the other side. I get M inverse here, X here, D, X inverse M, right? So I've multiplied on the left by M inverse and on the right by M. And what we get is sort of difficult to see, but what we have is I can write this as X inverse M whole inverse times D X inverse M. So this is sort of my new M matrix, which is telling me I can maybe write this as P equals to, this is N inverse, or maybe if you want to keep it in this same form, then instead of writing this as an inverse, M inverse X, I can write this as M inverse X whole inverse. Remember, if you're taking the inverse of a product, then you have to change the order, right? And so this gives me M inverse X. So I can write this as N D N inverse. Okay, so B is similar to D as well. So they're all in the same family. And what we mean here is that this is the nicest member of the family because it just gives you a basis of independent eigenvectors, the nicest member of the family. Okay, but recall that this is only possible when A is diagonalizable. What if A is not diagonalizable? Okay, and so that's the next problem that I want to discuss. And I'll just give you the answer of what you can do in this situation. So we consider two cases. Let's say, as an example, let's consider two cases in which, so when is A not diagonalizable? A is not diagonalizable when it does not have two independent or n independent eigenvectors, and that can happen only when A has repeated eigenvalues. Okay, so the idea is, let's consider A has repeated eigenvalues, and I'm going to give you a matrix that has this problem inside it, right? So if this is 3, 1, 0, 3, you can immediately see that this is an upper triangular matrix, which means that lambdas are just the diagonal entries. So my eigenvalues, lambda 1 is equal to lambda 2 is equal to 3. And clearly this is not diagonalizable, and I'm going to show you how this is not diagonalizable by showing you, by attempting to find a diagonalization, right? So how do we find the eigenvectors? So we try to find the eigenvectors, and you do that by solving A minus lambda I x is equals to 0. So I'm looking for the null space of A minus lambda I. And so this matrix is just going to be 3 minus 3, 0, 1, 0, 0 times x1, x2 is equals to 0, 0. Now this equation is just, well, the second equation isn't telling me anything. It's just telling me 0 equals to 0. And the first equation is telling me that x2 is equals to 0. So my eigenvector is just x1, which can be anything but a 0 on the second entry. So my only eigenvector that I have, and we can simplify this as x1, 1, 0, the only eigenvector that I have, so eigenvalues is lambda 1 is lambda 2 is equals to 3, but the eigenvectors are v is equals to 1, 0. Right, so I don't have a nice matrix in this family. There's no matrix, there's no diagonal matrix that I can make it similar to. I can imagine a diagonal matrix, but it won't be similar to that, right? So if I say 3, 3, 0, 0, in this case, let's say this is part of some family, right? So let's say this is part of some family which has some matrices inside it. Let's say this is my A matrix, right? And I want to see if I can write A is similar to this. So let's call this D, right? And I want to see, is there any such case? A is equals to MD M inverse, right? Now notice what happens when you try to do MD M inverse. The following happens. The diagonal matrix D, because it has the same entry on the diagonal, can just be written as 3 times the identity matrix, because it's just 1, 0, 0, 1 times 3. So it's just the identity matrix but scaled. So I can write this as 3 times I times M inverse, but then this scalar can just be written at the start, and this I doesn't matter. So you have M times I M inverse, and you end up getting 3 times M inverse, and which is just 3 times the identity. So if you try to find a similar matrix to this matrix, you just get the same matrix back, which means if I were to make a family, it would only have D in it. It doesn't have any other similar matrices, right? And this family, 3, 1, 0, 3, so let me just put a red sign here that say A is not equals to MDM inverse, because it turns out that any similar matrix to it is just this matrix. So if you think about in terms of family, this D matrix is all alone in its family, and this A matrix might have other members in the family, and you can try to find out. The important thing is that they will share the same eigenvalues. So here's one fact that I should have mentioned at the start, which is that similar matrices, actually let me just mention here, so similar matrices have the same eigenvalues, right? Because the idea is if they're doing the same transformation, then whatever eigenvectors you have here, they should be scaled to the same amount by both of these, right? The only difference is that the basis is different, right? So D is doing the same thing, but the nice thing about D is that it's doing it in terms of the basis in eigenvectors. So This family is different in this case. In the case when you have a repeated eigenvalue, right? So this is the case that we were dealing with. And so we see that maybe there might be a B matrix and a C matrix, but the D matrix, the nice D matrix that we're looking for, is in a different family. And so now the question becomes, okay, but what now? So if you have this family A, B, C, and I have this matrix in this family 3, 1, 0, 3, which one is the nicest member of this family? And the answer comes from the idea of Jordan form, right? So Jordan forms or Jordan block. And the idea is actually this A matrix is itself the nicest form because the Jordan form looks like this. So let's construct another example perhaps. So a Jordan block looks like this. A Jordan block looks like the following. If you have a repeated value, it's just the same repeated value lambda and a 1 here, right? This is a Jordan block. Another Jordan, this is a 2 by 2 Jordan block. A 3 by 3 Jordan block could be as follows: lambda, 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 1, 1, 0, 0, 0, 0. So this is a 3 by 3. This is a 3 by 3 Jordan block. And so the idea is that if you don't have a matrix that is diagonalizable, then you can put it into a Jordan form. And what's a Jordan form? So the Jordan form is the following. It's J1, J2, J3, so on, and the rest is 0. So this is 0 and this is 0. So it's just a diagonal matrix where J1, J2, J3 with Ji's are Jordan blocks, right? Let me give you an example. One example of a matrix in Jordan form is this, such as 3, 0, 3, 1, 0, 0, 2, 0, 0. If you try to look at this matrix, if I partition this matrix sort of like this, you can notice that this matrix is itself a Jordan form, is a Jordan matrix. And this matrix, because this is a 1 by 1, any 1 by 1 block in itself is a Jordan matrix. So a Jordan block rather, right? So I can view this matrix in terms of the 2 by 2 form, J1, J2, where this is a 2 by 2 Jordan block and this is a 1 by 1 Jordan block. And so you see this matrix is itself in a Jordan form, right? The idea is that you don't have diagonals on the matrix, you have diagonal blocks, these Jordan blocks on the, sorry, let me say that again. The idea is that you don't have numbers on the diagonal. The idea is that you have Jordan blocks on the diagonal. So this matrix is not diagonalizable. This is not diagonalizable. And the reason is that this repeated value just has one eigenvector. So each Jordan block corresponds to one eigenvector. Let's look at more examples. Another example can be the following. 0, 0, 0, 1, 0, 0, 1, 0. And this just has two entries in it, and it's very difficult to see how this is in Jordan form. But let me separate this. These ones give me an idea. There's no 1 in the third one. This is how you can view this as a Jordan form. So this is a 3 by 3 Jordan block, which has the eigenvalue of 0. And this has one eigenvector associated with it. And this Jordan block is a 1 by 1 Jordan block, which also has the eigenvalue 0. So if the eigenvalues are written down, they're just 0, 0, 0, 0. And the number of eigenvectors is what? The number of eigenvectors is how many Jordan blocks do I get? This is one Jordan block, this is the second Jordan block. So I have two independent eigenvectors for this. And it's easy to see if you try to find the null space, right? So there's a connection between finding the eigenvalues for this one, and it's the same as finding the null space. It's not always true in every case, but for this case, when you have 0 as the eigenvalue, it's exactly true. Okay. So that's the idea of a Jordan block. And so the statement is that the sorry about that, we had a network issue. Let's see if everything is working again. I will be right back. I want to fix a few things with the stream. Okay, I'm back. Let's see if the stream is working. Okay, so I have a question. Does that also mean identity matrices are a Jordan form of matrices? Okay, so they are, let me correct what you mean. So let me correct that. So the first statement that I would like to make is that all matrices, all diagonal matrices are in Jordan form. For example, if I have a matrix like 2, 2, 3, then this matrix is in a Jordan form because it contains three different Jordan blocks. This one, and this one, right? And you can see that it has three independent eigenvectors as well, which are just 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? And identity matrix also forms in the same domain, right? Identity matrix is just a diagonal matrix with ones on the diagonal and zeros everywhere else, and it just has Jordan blocks, right? And so the thing that I wanted to leave you with is the following fact, is that all matrices are not diagonalized. Well, let me say some matrices cannot be diagonalized, right? And these are the matrices which do not have those which do not have n independent eigenvectors, right? That's the first thing. That's something that we've already seen, that you can't diagonalize every matrix, but all matrices can be written in Jordan, sort of, I'm making this name up, in Jordan diagonal, can be Jordan diagonalized, if you allow me to use this term. And the idea is basically you can find some matrix such as, so in diagonalized means A is equals to X the X inverse, right? So let me put A inverse, I'll put an inverse sign there, something like this maybe. Okay, but Jordan diagonalization means this, in this case, this is a Jordan, this is a diagonal matrix, but the Jordan diagonalized means I can find some M times some J times some M inverse, and where I'm saying that this matrix, let me put a nice minus sign on both of them. So what I'm saying is this is not possible for all matrices, but this is possible where J is in Jordan form. And actually, the diagonal matrices are also Jordan forms, but they are Jordan forms with sort of, if you think about it, if it's a diagonal matrix, right? If this is J1, J2, and J3, it's just the Jordan diagonal is the same as the diagonal of the original matrix. Okay, so I hope that answers the question. And so yeah, so the thing was that these families, when you considered them, that these families have, so in families which don't have a nice matrix, right? So if I make a family of matrices A, B, C, these are not diagonalizable, right? A is not diagonalizable, then the nicest member of this family is J, because it's almost diagonalizable. It's almost diagonalized. It just has those annoying ones on the first off diagonal, right? And all of these matrices are similar to this Jordan form, right? I believe it's also called the Jordan normal form. And that's the best you can do. I can't diagonalize every matrix, but I can Jordan diagonalize every matrix, right? So this is something that you can do. So if you have A, I can write it as M, J, M inverse, where J is just some matrix which have Jordan blocks, J1, J2. And remember, these are not just one number, these are block matrices, so Jn. And actually, let me just put that as Ji, where I is the number of independent eigenvectors. Okay. All right. Let's move on to the second topic for today, and the topic that I've actually labeled this video with, which is singular value decomposition. I'm going to leave you with the Jordan form here. I'm not going to do any computations on how to find the Jordan form. I believe we've sort of run out of time and we don't have time to discuss that, but I just wanted to let you know that this is something that's possible and something that you should know about matrices that you can't diagonalize. Matrices that you can't diagonalize can be put into this Jordan normal form. That's the best you can do. And now we can talk about our second topic, our main topic for today's class, which is singular value decomposition. And this is sort of the culmination of each and everything that we've done so far. It's the culmination of all the ideas we've discussed so far. And here we're going to deal with any general matrix A, right? So it can be an M by N matrix. And this topic is going to bring together ideas from eigenvalues, ideas from symmetric positive matrices, ideas from the four fundamental spaces, subspaces that we looked at. So if you remember the four fundamental subspaces, which was the row space and so this was my row space, this was my column space, not the column space, this is the null space of A. And we had over here the column space or C of A, and over here we had the null space of A transpose, right? And this is an Rn space and this is an Rm space. And in the video, in the linear transformation video, something that I did not discuss in detail, but something that I believe I left the 3 blue, 1 brown video to explain, is that you can view this A matrix sort of taking you from Rn to Rm. So you're taking vectors from the row space to vectors in the column space through A. A is that linear transformation that you do. Okay, so what's the idea? How do we factorize something that's so general? And the goal for today, the singular value decomposition, the goal is to find there is a nice factorization that you can do for any general matrix of the form U sigma V transpose. And there are some properties of these matrices. U itself is an orthogonal matrix. V is an orthogonal matrix. If you remember what orthogonal matrices were, orthogonal matrices had this nice property that Q inverse is the same as Q transpose. So when I say V transpose, it's just the inverse of V, right? So if you think about it, this is very similar to, if I put X, D, X inverse, X, well, we did a Q, D, Q transpose, if you recall, which was for a square symmetric positive definite matrix. And now this is sort of a generalization of that idea into rectangular matrices as well, right? So this is sort of in some analog with this and some analog with this and some. So here we need two different matrices, and the reason is that this is an M by N matrix, right? Okay, so the dimensions of these matrices, I believe, are this is an M by M matrix, and this is an M by N this is an M by N, this is an M by N, and this is an N by N matrix. So if you combine all of these together, you get an M by N matrix. Okay, what is sigma? Sigma is a diagonal matrix, and it contains sigma 1, sigma 2, some diagonal entries, and sigma n, and it may contain some zeros as well, so 0 perhaps on the diagonal as well. And we call sigma i's are the singular values. So these are also analogous to what you get on the diagonal matrix of D, which were on D you have the eigenvalues, and on sigma what you have are the singular values. So this was an n by n case where you do this, and here A was FPD, right? Here we don't know anything about it, but we're hoping that we get this transformation. So we get this factorization of A into these subcomponents. Okay. So before I start telling you what this is, let me show you another form. Before I start telling you how to compute it, let me tell you what they represent. So what these all matrices contain and another way to view them, right? So if I have U sigma V transpose, I can write this as A times, if I put V here, multiply both sides by V. I know that V transpose V, because V transpose is the same as V inverse because it's an orthogonal matrix. This is just identity. So I get AV is equals to U sigma. And let's write this out. This matrix A has some matrix, while V has some column vectors V1, V2, up until how many do we have? We have n by n, so we have Vn of these, right? And U is U1, U2, Um, and then this being multiplied by these singular values, which are sigma 1, sigma 2, dot, dot, dot. And this is not a square matrix, by the way. This is an m by n matrix. So in general, sometimes it might be a square matrix, but mostly it will be a rectangular matrix where either there are more rows than columns or more columns than rows. But what is this equation really saying? So it's saying if I interpret each of these columns separately, it's telling me something like A times V1 is equals to sigma 1 times U1. I'm just looking at what one column is giving me on the other side. And what it really is telling me is that, let me just write it, AVI, sigma I UI, is that what are VIs? I can think of VIs. VIs are the orthonormal bases of Rn, and UIs are the orthonormal, or let me just say the row space, and UIs are the orthonormal bases of the column space. So what I'm looking for, because I say that these are orthonormal bases for two reasons. Firstly, let me correct what I was saying. Let me add some missing pieces that I might have glossed over. Because these are orthogonal matrices, their columns will be orthogonal, right? Orthonormal, rather. We can choose them to be normal, that is, they have length 1, and they are orthogonal to each other, which means that you have a set of independent matrices, right? So if I look at it in terms of this picture, what I really have is I have unit vectors V1, V2, and unit vectors U1, U2, but the equation that says AVI is equals to sigma I UI is saying that this transformation from this row space to this column space is going to give me some multiples of these orthogonal unit vectors, right? Actually, over here we can also consider what's going on in the null space. What about these ones, right? If there's some vector here, let's call this n1, then A times n1 will just give me some zero matrix, right? This is just going to give me 0, or rather, let me just so A times n1 is going to give me 0, which is just 0 times any UI, right? So it's basically the null space, right? So it's mapping whatever is in the null space to 0, and the singular value corresponding to that. So this is sigma I. So singular values corresponding to the null space are equals to 0. So when I said they might have some zeros in here, they're coming from the null space of A. Okay. So this is a transformation that is taking Rn to Rm, and we're looking for really these orthonormal bases for the row space and this orthonormal basis for the column space to give me sort of this transformation, this factorization that I'm looking at. And these UIs, by the way, these are in the null space of A transpose, right? So what's happening is that these unit vectors, the scaling of these unit vectors is becoming 0, right? They're shrinking down to 0. So this sort of, you can think about that this null space of A transpose is shrinking down to 0. Okay. All right. So let me now tell you how to compute this factorization. So how do we compute A equals U sigma V transpose? Now, this is 3 different matrices that we have to find, and there's no immediate way of trying to see it because this is an m by n matrix. So if I want to break down A into 3 different matrices, I can't see how I could go about doing that. But there is a nice little multiplication that I can do. What about A transpose A? Okay, A transpose A is U sigma V transpose whole transposed times U sigma V. What do I get over here is V transpose transpose. Of course, you have to change the order. Then you put transpose on all of these matrices, U sigma V. Recall that U was orthogonal, which means U transpose is the same as U inverse, which gives me V transpose. Well, V transpose transpose is just V. Oops, I missed a transpose here. Okay, and so I have by the way, sigma transpose is just sigma, right? Sigma is a diagonal matrix, which means when you transpose it, you get a square matrix. If this was m by n, now it becomes an n by m matrix with diagonals. So let me just give you an example, right? So if I had sigma 1, sigma 2, and then 0, and let's say this was it, 0, 0, 0, 0, 0, then its transpose is going to be sigma 1, the first column is sigma 1, 0, 0, and the second row is 0, sigma 2, 0. And now if I multiply them together, this was m by n, this was n by m, what I will get is an n by n matrix. I'll get sigma 1 squared and sigma 2 squared. I believe that's right, right? Sigma 1 squared, 0, 0, and then 0, sigma 2 squared. So I get this nice little n cross n matrix, right? So this is just sigma squared. I'm going to call it sigma squared now. V sigma transpose, so A transpose A. Notice what happened. This has become the factorization. This has become the diagonalization of A transpose A, because this is just an orthogonal matrix. This is just its transpose, and this is just some D. This is the same as saying ATA is equals to Q D Q transpose, for what we used to do for a symmetric positive definite matrix. Okay, so ATA is now just a diagonalization problem. So here's the important fact that we found out. A m by n was not diagonalizable, but A transpose A, let me remove this, is diagonalizable. That's the first thing that we know. Okay, so let me just put the transpose sign, so A transpose A is diagonalizable. Okay, and so what is this? What are these V's? These V's are the same as the one we had for A, but what about this sigma squared? This will now have, so the eigenvalues, if this is a diagonalization problem now, then you will have lambda 1, lambda 2, dot, dot, dot. So basically the eigenvalues, but these are now the same as sigma 1 squared, sigma 2 squared, and so on. So the eigenvalues of A transpose A are the same as the squares of the singular values of A. So if you find the eigenvalues of A transpose, something that you already know how to do, then you will have the squares of the singular values, so you can just square root them. So let's say A transpose A has eigenvalues lambda 1, lambda 2, then A will have singular values. Sigma 1 will be square root of lambda 1, and sigma 2 will be the square root of lambda 2. So I'm just reversing the square that is happening. So here's the procedure that you do to find. So the first step that you find is to diagonalize A transpose A. So diagonalize, let me put A pen here. So transpose A. So we diagonalize A transpose A, that's the first step. And the eigenvalues are the squares of the, so I can maybe write it as take the square root of the eigenvalues to get the singular values. That's the first step. And within this step, you also find the eigenvectors. The eigenvectors give the columns of V. So you've done, in this first step, you've already found two things. I wanted to do A is equals to U sigma V transpose. And when I did A transpose A is equals to V sigma squared V transpose, I not only have sigma, because I know all the singular values now, I also know V. So these two, so this allows me to find V and sigma. So it's just a diagonalization problem now. Find the eigenvalues, find the eigenvectors, you're done with sigma and V. And so the only problem that's remaining is U. And for U, we do a similar thing as we did just right now for V. For U, what we do is, let's do, instead of A transpose A, we're going to do A transpose. So that's going to be U sigma V transpose. And in this bracket, we will have U sigma V transpose, whole transpose. So we get U sigma V transpose, V sigma transpose, U, I believe it's U transpose. And so we have U, this becomes the identity. So U sigma squared, U transpose, A, G. So again, instead of solving for U, we're now going to diagonalize. We're going to diagonalize A transpose. So here's a nice little summary. If I want to add to it, the second step is going to be, and let me just copy all of it, and let me put it in a nicer place. Let me put this over here. Yeah, so I'm going to put this over here. Diagonalize A transpose. And what are you going to do? We are going to do, the next step is going to be diagonalize A transpose to find U. And let me just add the transpose signs now. So this is A transpose A, and this is A transpose. And you have U. So this step, this gives you sigma and V, and this gives you U. But notice that it also gives you sigma squared. You already know what the eigenvalues are, so you don't need to solve for the eigenvalues. If you've done the previous step correctly, then you can just fill it out and then solve for. So just in this step, you just need to find U's lambda 1, lambda 2 to find the eigenvectors. That is the column of U. And that's it. That gives you the factorization of A is equals to U sigma V transpose. So this basically boils down to solving two diagonalization problems, solving two diagonalization problems, which are as follows. The two diagonalization problems are A transpose A is equals to V sigma squared V transpose, and A transpose is equals to U sigma squared U transpose. And that's it. So that's the best thing that you can do for the general A matrix. With an M by N matrix, that's the best that you can do. Okay, so I'm going to stop here now. I'm not going to do any example. Have I said what I needed to say? Yes, I believe I have. So I'm not going to do an example. I'm just going to discuss some ideas. And one thing that I would like to do is write down all the factorizations that we've done. So we did A is equals to CR, we did A equals to LU, we did A equals to, and well, this was the same as LDU as well. We did QR decomposition, we did A is equals to X dx inverse. For symmetric ones, you can do Q dq transpose. And now we did the singular value decomposition, which is U sigma V transpose. So these are all the factorizations. I mean, linear algebra course should also be known as just like a course of matrix factorizations, right? That's really all we're doing. And the reason that we look at all these factorizations, I want you, at the end of the course, if I want you to have some takeaways, is to think about when each of these factorizations are possible, how do they make computations easier? These are the questions that you should be asking yourself. Where are they used? Right? And perhaps what linear algebra ideas are used to construct these factorizations? So when I say linear algebra ideas, I mean ideas such as eigenvalues, linear independence, orthogonal vectors. These are ideas that are related to vectors, but you constantly employ to find these different factorizations, right? So yes, that's the end of the course. These are the factorizations that we've done, and each of these is really helpful. Each of these makes our lives easier when we're dealing with large matrices, and it really depends on, actually let me put a couple of things here as well, symmetric matrices and positive definite matrices. Yeah. So, and even ideas like column space and row space. Okay. So that's it. That's the end of this course. There's one technicality that I sort of brushed over here, is that there are, in this one, let me just finish this technicality. So let me say the following now. Over here, this was not exactly true. I have sort of glossed over a bit of ideas, is that if Rn is an n-dimensional space, then the row space will only have R dimensions, right? So from V1 to VR, you will get orthonormal basis for row space. U1 to UR are the orthonormal basis of the column space. Recall, if I'm just talking about the dimensions, right? So if this is rank, so the dimension is equals to R, the dimension is equals to R, then this has dimension N minus R, and this is dimension M minus R. So V1 to VR are the orthonormal bases for the row space, and VR plus 1 to Vn are the orthonormal bases of the null space of A, and UR plus 1 to UM are the orthonormal bases, or rather, let's say, is the orthonormal basis for the null space of A transpose. So we started off with these four fundamental subspaces, and we've now given the best thing that we can do is that we can find some orthonormal basis for each of them. And so an orthonormal basis for the row space, null space, column space. And so this is perhaps the nicest sort of factorization that you can do. Okay, that's it for linear algebra course for summer 2020. This was the last thing that I wanted to do, and I believe our course is done. Okay, hope all of you learned something. That's it.